satisfactory one-man class.
No, actually I want to watch some Studio C videos with you. I got a couple ones that are just like, they're the worst, and I love them. All right, so for those of you on the live stream, this is the solution to the problem. Hopefully you can read my handwriting. I'm going to give you a second in case you want to screenshot that. But you can always rewind the video or pause it, so I won't give you that long. What we're going to talk about now is power calculations. So the thing about power calculations is that power calculations are kind of one of the most important pieces of this class. As I said in the 2 lectures that I posted, one of which you actually survived, the issue with power calculations is that power is for the sake of this class, it's one of the most important pieces. As we've mentioned before, the power equation is P is equal to V times I. Okay? And this is, or you could write it like PIV, P is equal to I times V. Some people like pronouncing that PIV. I don't care. But power is equal to voltage, instantaneous voltage times instantaneous current. Okay? This does end up being a function of time, just because both voltage and current are also functions of time. So if you want to calculate the power at any time t, you have to find out what the voltage and the current is at that time, and then multiply them together. Okay, so here, let's say we're going to go to a very, very simple circuit. Okay, this is going to be Vs, and with Vs, we're going to say this is 12 volts. Okay, and then we'll have 2 resistors. This will be R1. VR1 we'll say is equal to 6 volts. And then we've got R2, and VR2 we'll say is equal also to 6 volts. Okay? Now the question is, can you figure out the power that's being consumed in this entire circuit? And the answer to that is no, because while we don't know what the voltages are, we don't know what the currents are. We have to know what the currents are. So if I just say, all right, we have one loop here. In loop 1, our current is going to be equal to 0.05 amps, something like that. And then the question is, how much power is being consumed by every component? Okay. Before we get started, anytime I start an equation, anytime I start an example, I always start by doing KVL and KCL. Okay? You're going to get used to that because every problem is solved with KVL and KCL. Absolutely every circuit problem is KVL, KCL. It's just, you start breathing it after a while. Making sure that it shows up on camera. I feel like the frame rate's really low. Could just be my computer. Whatever. I guess I'll have to watch the video later and see if it sucks. Alright, so KVL here. We'll start by identifying positives and negatives. Positive, negative, positive, negative. We'll then identify the loop. We've already done that. There's only one. We'll then identify the nodes. 1, 2, 3. Okay, so for loop 1, which there's only one loop, we have Vs is equal to VR1 plus VR2. We already know that because I gave you the voltages, but that's easy. For KCL, you have node 1, which is this one here. Node 1 says that IS is equal to IR1. Node 2 says that IR1 is equal to IR2. And then node 3 says that IR2 is equal to IS. So that really didn't tell us all that much. I mean, it tells us everything, but we You can kind of figure it out if you just stare at it for a while. And the thing that we know about all of these is that they're all equal to 0.05 amps. Okay? So the question is, how do I figure out the power going through Vs? You multiply the voltage Vs by the current going through Vs. What is Is? So power in the source that's coming out of the source, being put into the circuit, is equal to the voltage across the source multiplied by the current through the source. Okay, I've already given you the voltage across the source is 12 volts. I've already given you that there's one loop, and based on these equations, all of the currents are the same, which means in that one loop, you have 12 volts times 0.05 amps. So the total power that's being produced, that's being put into the circuit by the power source, is going to be equal to 0.6 watts. Okay? Now, question. If I add the power that's being consumed by R1 and R2, am I going to get 0.6 watts? Why?
Take away 0.6 watts by the end.
Conservation.
It all has to do with the conservation of energy. You're right. But the thing is, when we came up with KVL, we established that energy has to be conserved in the circuit. If we're putting 0.6 watts of power into the circuit, we're not accumulating power in this circuit. Okay? If we are, this thing is going to start heating up. It's going to start turning into heat. What we have is 0.6 watts is being consumed by the rest of the circuit. Okay? It will always be this way. The amount of power that gets put into a circuit will always be equal to the amount of power that gets pulled back out of the circuit. If it starts turning into heat, it's because a certain amount of voltage is actually being applied across a wire. Anytime you plug in a paperclip into a power outlet, you're turning that paperclip into a resistor, and you're causing 120 volts to go across what is basically a line. Has a very high current and a very high voltage, which means you have a very high power draw, which is why it sparks. Because all of a sudden the power draw from that outlet just skyrockets. By the way, the resistance, oh, we'll get into that. That's a next week thing when we talk about resistance-only circuits. When we're talking about power here, we should expect that the amount of power going in is equal to the amount of power going out, okay? That's a KVL principle. We should see that that's true here. So now the question is, what is the amount of power in R1? And what is the amount of power in R2? They're both the same because the numbers are all identical.
0.3 and 0.3 watts.
Yep. And that is because VR1, which is equal to VR2, times IR1 is equal to, this is 6 volts, 6 times 0.05 amp, 6 volts times 0.05 amp, and that's just equal to the 0.3 watt. Okay, so all of the components in the entire circuit, their power consumption adds up to the amount of power that's being produced here. Okay, now a few of you have already mentioned, well, can't you just do equivalent resistances? Yes, you can do equivalent resistances. Equivalent resistances is one way of solving this circuit. Okay, we're going to be using equivalent resistances to be able to figure out what the circuit behavior is without giving you the voltages or the current in here. If I just give you Vs and what the resistances are, you're going to have to be able to solve the circuit. Okay, so if I were to turn around and instead of giving you this, be like, okay, here's Vs, and Vs is 10 volts. This is R1. This is R2. And R1 is going to be equal to 50 ohms. And R2 is going to be equal to also 50 ohms. What is the power being produced by VS? You're going to have to be able to figure that out. Okay? Now, you shouldn't be able to figure that out right now. We're getting there. But this is where we're headed. You need to know not only how much power is being consumed by this resistor, but also how much power is being supplied. What are those power values? In order to figure out the power values, you have to figure out the current. Here, you don't know what the current is or the voltage is across this component. You only know the resistance. And you know that it's plugged into a circuit that has 10 volts put across it. Okay? Not quite.
No?
Nope.
Oh, no, yeah, you have to do the entire.
Yeah, you have to do the entire thing.
That's more math than I'm really doing.
What do you mean you have to do the entire thing?
Here, the amount of voltage that's going across this, because this is a resistance component, V is equal to IR. So here, you know that this component, the voltage from VR1 plus the voltage from VR2 is equal to VS. So because of this V value is not equal to VS. So it does shift things a little bit. Okay, and yes, you can solve this with a matrix. We won't, but you can. I'll show you a little bit about how to do that, because it's really not that hard. Honestly, the equivalent resistance method is more challenging than the matrix method, believe it or not. But you have to be really good at setting up matrices, and you have to be really good at plugging them into a calculator. So if that's hard for you, yeah, that's just not fun. Anyways, the whole goal of moving forward from here is we now understand how to set up the equations, okay? This piece, you should know how to do this. The end of this week, this should be easy. And maybe not easy, but this is what we learned this week. This is everything that we've done has derived to this. You already know the equations. You know Ohm's law. I've given you the equations for capacitance and inductance as well. We will be using those. You got to be very comfortable with your equations, and you have to be very comfortable with writing the equations out. Starting next week, we're going to start solving problems like this. This is an easy problem. Okay, Jeremy can do it in his head almost. He just doesn't want to. He chooses not to. But we're going to be starting to solve problems like this. Okay, and then it's a question of what is the power in the source? Okay, how do you figure out the power in the source? Well, first you have to figure out how much current is going through both of these resistors. Once you figure out how much current is going through both of these resistors, you know how much current is going through your source. Once you know that, you know how much power is being produced by your source. Once you know how much current is going through here, you can figure out how much voltage is being applied across each one of these resistors. It's stepping through your system. Basically what you do is, by doing the equivalent resistance method, you start with a very broad, generalized picture of what's happening at the source, and then you slowly build out into individual components until you get really, really detailed. But that's what we're going to be doing next week. You will have a quiz that's posted on Canvas online. I will try to get it put online today. I am going to start assigning reading assignments for next week. That said, not everybody's going to have your book by next week, so if you don't have your book, get it done in by 2 weeks or borrow somebody else's book. Outside of that, there is no homework in this class aside from reading assignments and quizzes. Now, do notice your quizzes are basically taking the place of your homework assignments. You have one try at all of them, and you will either get a pass or fail on each question. That's the way that I set up my quizzes, okay? If I were you, I would take time on your quizzes. Come in and ask questions. Don't hit the submit button until you feel confident in your answers.
Can we go backwards after we click on question?
Yeah. Once you submit, it's done.
So I can check the questions. So I can move
Yeah.
without transfer.
Right, without hitting submit. Yeah, all the questions will be 1 page. Yeah.
So can we use our book?
Yes. And you can even use each other if you really want to. It's kind of, yeah, it's like I said, the quizzes are taking the place of homework. But the nice piece about this is that I don't have to grade your homework. Yeah, I said that on YouTube. Take that!